Welcome back. Today, we are cracking open the engine room of mathematics. We're going to be talking about the logic of proofs. You know, the super precise, unbending language that mathematicians use to build arguments that are just absolutely airtight.
So here's the big quest we're on. Our ultimate goal is to tackle one of the most elegant proofs in all of math, proving that the square root of 2 is an irrational number. But here's the deal with mathematical proofs. You can't just wing it. They follow a very rigid set of rules. And to even attempt this proof, we first have to master the rulebook.
So, let's start building our toolbox. Our very first tool, and honestly the most important one, is the fundamental building block of pretty much every logical argument, the if-then statement. And probably the best way to think about it is as a kind of promise. Now, in logic, we call this an implication. It's got two parts. We have P, which is the premise, that's our starting condition, and that leads to Q, the conclusion, the result that's supposed to happen. So P implies Q. Sounds simple, right? Well, mostly.
To make this less abstract, let's use a real-world example, kind of like a social contract. Imagine a student named Andy makes this promise. If it does not rain, then I will go to campus. Okay, so in this case, our premise, our P, is it does not rain. And the conclusion, Q, is Andy goes to campus.
Now, think about this. How can Andy break this promise? Well, if it doesn't rain and she goes to campus, she kept her word. Great. But there is only one specific way for her to break it. If the premise happens, meaning it does not rain, but the conclusion fails, she decides to stay home anyway, then and only then is the promise broken. This is the single critical failure state that makes the whole statement false. Okay, so we've got it figured out for a sunny day. The promise is either kept or it's broken. But what if it rains? And this is where we find a really fascinating logical loophole. Think about it. Andy only made a promise about what she'd do on clear days. She never said a single thing about what she would do if it rained. So if the premise is false, if it does rain, her promise can't possibly be broken no matter what she does. Whether she goes to campus or stays home in the rain, her original statement is still considered valid. In logic, this is called a vacuous truth. So this brings us to the golden rule, the one thing you really got to burn into your memory. A statement P implies Q is only, and I mean only, false if a true premise leads to a false conclusion. True to false equals false. Every single other combination is considered true. All right, we've got our first tool, which is awesome. But now we have to talk about a super common trap, a fatal flaw in thinking that our brains just love to fall into. It's this natural urge to just reverse the statement. You know, we hear if P, then Q, and our intuition just screams, well then, if Q, then P must also be true. This flipped version is called the converse. But listen close, they are not the same thing. Assuming they are is a critical mistake in a proof. Let's make this crystal clear with some simple math. On the left, we've got a perfectly valid statement. If x equals 2, then x squared equals 4. Yeah, no argument there, that's definitely true. But now, look at the converse on the right. If x squared equals 4, then x equals 2. Is that always true? Just take a second and really think about that one. And here's the proof that it fails. What if x is negative 2? The premise, x squared equals 4, is totally true. But the conclusion, x equals 2, is false. And there it is. We've found our killer combination, a true premise leading to a false conclusion. And based on our golden rule, that means the entire converse statement is false. They are not the same. So if we can't just reverse a statement, are we just stuck? No, not at all. Logic gives us this awesome tool, a kind of secret passage. It's a perfectly valid way to manipulate an implication, and it's called the contrapositive. So we've established that just flipping P and Q around is a big no-no. But that raises a pretty important question. Is there any valid way to rearrange the statement and have it mean the same thing? And the answer is a big yes. It's the contrapositive. Here's how you do it. You flip the terms, and you negate them both. So if P, then Q, becomes if not Q, then not P. And here's the magic part. These two statements are always, 100% of the time, logically identical. But wait, why does that work? Let's do a quick test. Remember, any implication only fails if true leads to false. So for the contrapositive to fail, its premise, which is not Q, has to be true, and its conclusion, not P, has to be false. Okay, let's just translate that. If not Q is true, well, that just means Q is false.
And if not P is false, that means P must be true. So the failure condition for the contrapositive is P is true and Q is false. Wait a minute. That is the exact same failure condition as our original statement, and that's why they're equivalent. And with that powerful little realization, we've basically assembled our logic toolbox. We now have the core tools we need to actually start building our proof. So why is this so important? Why do we care? Because the contrapositive is like a backdoor. A lot of times, trying to prove a statement directly is like trying to bust through a door that's chained and bolted shut. But proving its contrapositive can be like finding an unlocked door right next to it. And since they mean the exact same thing, proving the easy one also proves the hard one. It's a game changer. So let's do a quick recap of our complete toolbox. First, the golden rule. An implication is only ever false if true leads to false. Second, the converse fallacy. Don't you ever assume that just flipping it to if Q, then P is true. And third, our new power tool, the contrapositive. If not Q, then not P, is your secret backdoor to the truth. We now have the logical key. The door to proving that the square root of 2 is irrational, it's standing wide open in front of us. The only question left is, are you ready for the proof?